Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the most awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Sam Hadden and Dan Tamayo with us today. Hey, Dan. Hey, Sam.
Hello. How's it going?
Good. Sam, let's start off with you. Where are you located at these days?
I am at the Canadian Institute for Theoretical Astrophysics in Toronto, or CETA. I've been here for about a year now as a postdoc.
Cool. Let's see, it's November 9th of 2022 as we shoot this, and is late fall, early winter in full bloom at CETA, Toronto?
Winter is creeping in.
But not enough you can still ride that green bike. I see there, a green-yellow bike there in the right corner.
That's right. I try to bike all the way through the winter. But you know, nice. Canadian winters can be punishing. So
what's your
my resolve falters in February.
So what's your distance from home to office?
It's about 20 minutes on bike.
Okay.
So a nice ride.
Very cool. No, very nice.
I was at CETA before also. That is hardcore. It is only a select group that bike all winter.
Very good. Very cool. And Dan, I imagine the weather's a little different where you're at. Where are you
at? I'm in Claremont, California, at Harvey Mudd College. I just started here this fall.
Very cool.
The weather is amazing. Very different.
Southern California. Although I do admire that picture of Jupiter over your head there. That's an awesome shot.
Thanks. Yeah, this was my favorite picture from all of space in grad school. I worked with the Cassini mission. And,
okay. Nice.
I wasn't involved, but my research group planned out these observations as the spacecraft passed behind Saturn. It doesn't even look real.
Beautiful. Hey, I noticed that chair next to you has like a little bike symbol, a little white bike symbol on it. Is that what that is?
This is a really old Harvey Mudd chair. That's the old Harvey Mudd logo.
Ah, that's the logo. Got it. Still looks like a bike. I think it is. So we're in bike mode here. We've got bikes all over the place. So very cool. And Sam, what do you like to do for research?
My research is sort of generally in the area of planetary systems, principally exoplanets, but I'm interested in solar system stuff as well. And I mostly focus on dynamics and sort of celestial mechanics. So in other words, understanding how systems evolve under their mutual gravitational interactions. I guess this has the distinction of being the oldest branch of astronomy and even physical sciences. But there's still lots to do even after 3 centuries plus. So.
Yeah, and AJ was actually founded by a celestial mechanicist. So it's got a long, distinguished history in AJ. And Dan, what do you like to do for research?
I have very similar interests to Sam. Yeah, interested in trying to understand especially the early stages of planetary systems after the disk goes away. Times that we think are chaotic and quite violent, trying to understand the dynamics there. So both on the theory side and developing numerical algorithms for integrating those differential equations.
Very cool. And that is going to bring us to this very awesome AJ article, Celestial Mechanics. AJ, it's open access, people. You can go get a copy for free, so go ahead and get it. And celmech, a Python package for celestial mechanics. And Sam and Dan, take us away.
Yeah, sure. So this is a code that has been in various stages of development, maybe even since 2017 or prior. In a sense, it's kind of became a COVID project.
Yes.
Most of the bulk of the work was done during COVID. And it's a package, as the abstract says, for all sorts of different celestial mechanics calculations. And what I mean by that is, there's all these wonderful modern codes like Rebound for doing direct in-body simulation.
Right.
But the other side of doing in-body dynamics is sort of analytic calculations. And the reason one might want to do analytic calculations, why are they useful when we have these wonderful numerical simulation tools around, is that that gives you some insight into the actual dynamics that you might be studying in any particular system. And I think it's especially important because any sort of problem that you confront in solar system or exoplanets is typically an inverse style problem where you're presented with some set of
right
observations of the present orbital state of, say, some planetary system, and you want to know what are the potential dynamical histories that they could have brought it into this state. And it might be easy enough to find a numerical simulation that gives you a particular, that can, there's a wide space of initial orbital configurations to explore, and you might be able to find one particular numerical example that reproduces what you see. But we're more interested in understanding the full range of possibilities that so it's a sort of high level reason for taking this approach to celestial mechanics.
Cool. Nice.
And so and this was an attempt to make a sort of open source code that could be applied to these sorts of problems.
Okay.
I
like
feel like
source codes.
I feel like that's been sort of a exciting trend over the last decade, right? That there's all these open source codes.
Yeah.
So we don't spend your entire graduate career reinventing the wheel and then doing one extra thing.
Right.
We can sort of specialize and build these tools so that more people can do exciting science.
Exactly. Very good. So what I imagine other people have put out celestial mechanics packages, maybe not in Python. So what are some of the and I'm sure we'll get into it here. What are some of the unique features of celmech?
Yeah, I mean, I'd say that like just big picture, the sort of open source versus developing your own tools is extra challenging in celestial mechanics just because there has been this build up over 300 centuries of this formalism. And right, usually the way it's gone is you have groups that have like their own proprietary codes, either because they want to work on things themselves or just because there's a lot of work that goes into developing and supporting codes that other people are actually able to use.
Especially supporting these.
So, I think it has been challenging to get your hands on these types of codes to be able to attack these sorts of problems. And I think celmech actually fills a pretty big gap there.
Good. Very good. Okay. And we'll probably get into Rebound and what the relationship is, but let's go ahead and do a simple example. Who wants to cover a simple example?
Sure, I'll talk about a simple example. So we started the paper without a nice introduction to, seeing what this code can do and what it's for is to, and how one might use it is to walk through an application. We sort of set up a hypothetical planetary system with a pair of, I believe, Earth mass planets.
Yes.
And for them to do something interesting, we choose to initialize them near a 3:2 mean motion resonance, or this is a orbital configuration where their orbital periods are related by a ratio of 3:2. So the inner planet will orbit about 3 times every time the outer one orbits twice. And as a consequence of this, their mutual gravitational interactions have a chance to sort of add coherently over time. And so while the gravitational force from a planet relative to the force felt by the star is tiny, this ability for them to add their perturbations coherently can lead to dramatic behavior on sufficient timescales. And this is the sort of dynamical situation that in order to understand, one would turn to the sort of analytic theory or semi-analytic theory that celmech is designed to help you do. And you mentioned rebound and celmech's relationship to rebound. So rebound is a popular n-body code, and we've designed celmech so that it interfaces closely with rebound, in part because of so many people are familiar with rebound, and also it just provides a wonderful interface for sort of setting up the calculations that one would want to do with this code. And I think you see in this first code snippet that we've put in the article, we're setting up one of the sort of fundamental Python objects that celmech is designed to work with. So, Poincare object, named because of the set of variables named after Henry Poincare, because it works in variables that are, I think he first derived, or at least carry his name. And so what we do in that code snippet is actually set up our celmech object directly from a rebound simulation, which is represented by this sim object that we've assumed the user is already set up, or is, I believe, set up in the Jupyter notebook that we link to this code.
Nice.
And so we set up the objects in this code snippet, and then we show how one begins constructing a simple calculation using this celmech model in this first order approximation section. And so what one does, and this will be familiar to people who have done these sort of calculations, is in order to capture the dynamics, one adds individual terms from the so-called disturbing function. And so the disturbing function, which I think we'll see in gory detail later, is basically a multiply infinite cosine term expansion of the interaction potential between a pair of planets. And the reason one does this is that most of the terms in this multiply infinite expansion can be dropped when considering dynamics of a particular system, and they're dropped because first of all, most of them are quite small and make a negligible contribution to the dynamics, and also their arguments are rapidly oscillating, so their net effect sort of averages out over time. And so here we have a code snippet that we're just going to select a couple individual terms from the disturbing function to add to our equations of motion, which are going to be carried around by our Hamiltonian object, the Poincare Hamiltonian, which we've named HP in this example. And then the next equation shows a sort of encapsulation of the terms that we've added to our system so far. And so a small technical detail is that while celmech uses so-called canonical momenta and coordinate variables to do its sort of internal work, its integration of the equations of motion, for example, it's often more convenient to see things expressed in familiar orbital elements. And so this, in equation 1, is showing the terms that we've added in terms of orbital elements. And we see in equation 2, which we've hopefully labeled ND, the equivalent expression that one would get from what's sort of the standard reference in the sort of work, the textbook by Murray and Dermott.
Yes.
And so
Uh-huh.
you see that the eccentricity dependence between the two expressions and cosine terms appearing in them are the same, whereas they have some different names for the coefficients that come along with the cosines. And you can see there's a lot more numbers hanging off the top and bottom of our coefficients,
Right.
which seems excessive. But really, you need if you want to be specific
Yep.
about which terms you're including, you really need all this granular detail in that. Whereas it's hard to know unless you've memorized the appendix of Murray and Dermott, which I will admit to at least knowing on site what F27 and F31 mean. They would otherwise be sort of cryptic.
Right. Very good.
And so that's the setup. So we've set up our simple model by putting these two terms in our equations of motion.
Okay.
And you can see a result of the comparison, comparing integration of these equations to integrations with direct n body in our first figure here. So figure left panel just shows the system that we've set up. It's actually, we've added, I mentioned the 3 to 2 resonant planets initially, but there's an additional planet that we've added further out. It's not as closely spaced, and therefore its effect is not as dramatic. And you can see you get some decent agreement between our simple analytic model and direct n-body integration. We do a decent job of reproducing the amplitude of eccentricity oscillations of the middle planet.
Yeah.
And the frequency is, fairly well reproduced as well.
Lags a little bit. Yeah.
Lags a little bit. That's right. And so, depending on the level of detail that one wants, you're either satisfied with this sort of analytic approximation, or you could wonder, where's the shortcoming in our analytic model? Can we sort of pin down the approximations that we've made thus far that sort of have led to this disagreement? And so I think that brings us to the second order terms.
Okay, let's take a look at some of those. Those got, look at all these. Lovely. I love it.
So maybe so far, we've just taken the resonant interactions between the inner two planets. There's the third planet isn't even doing anything in the orange curves.
Yeah. So, right. This one way out here at, was it 3.2 AU, I think it was, or 3.2, something like that. What was it? I'll remember it when we set up the initial conditions, but okay. Second order.
Dan, do you want to describe what's going on at second order? I'll stick
sure.
with the giant mess.
Yeah, so I mean, this sort of traditional disturbing function expansion is typically done in powers of the eccentricities and the inclinations, because those are typically small parameters.
Mm-hmm.
So we want to go to second order in the eccentricities. You can see from that mess that you actually get a lot more cosine terms.
Indeed.
The other interesting thing that starts appearing at second order is that you get so-called secular terms.
Yeah.
Which you can think about as sort of playing the movie and fast forward and imagining the planet's mass smeared around their orbits and thinking about rings of interacting masses.
Ooh, okay. It's an interesting way to think about it. Okay.
That a long time ago, Laplace and Lagrange showed if you just consider those, that gives you like a system of coupled harmonic oscillators. Gets more complicated if you include resonances.
Right.
But when we go to second order, then those secular terms start appearing. Those are the ones that don't include any cosine whatsoever, or at least don't include any of the lambda variables, which are the that's the phase of the planet along the orbit. That's the angle that's just spinning around really, really quickly. So for example, the last two terms in equation 3, those are ones that just involve the angles that tell you how the orbit is rotating, and that happens much more slowly. So because those are slowly changing terms, again, they have a chance to build up coherently over time.
Cool.
So this is the place where we start introducing the effects of the third planet. The third planet is interacting secularly to leading order with our inner two planets.
Okay.
Anything to add there, Sam?
Yeah, so just on that, you can see that some subscripts now, maybe word on notation, the E's are the eccentricities of individual planets, and we see some subscript 3s indicating the third planet is now accounted for, and the S's are related to inclination. So another thing we had ignored in the first order model is that it matters that for the dynamics that the orbits are inclined relative to one another. But as a more general statement, if one were working on this sort of problem sort of without celmech, you would write down your first order model that we integrated first, and maybe that's not so bad. You go look up a couple coefficients in the appendix of Murray and Dermot or some other reference, and you code up your model, you integrate your equations of motion, and you produce something that looks like figure 1. Right. And if you want to figure out, well, maybe you ignored second order terms, but if you want to figure out if they're important, you see obviously that there's quite a few more terms to go look up in an appendix in equation 3. So at that point, you probably give up, or,
never
a grad student that does that for you or something. But now, it's a one-liner in celmech to add all these terms. And
that's awesome.
So now you can set up that higher order model and quickly check with integration, following the exact same procedure that we used for our first order model to see if that gets to the heart of the problem. Okay, now we're here at figure 2. We see it does, we're getting better. The second order model is now the orange curve, and the blue curve is sort of hiding under the green curve there.
Much better.
So we're getting better, and we have inclination evolution as well. And you can see that as I mentioned before, second order model is necessary to get any inclination evolution. But it's still a little bit off. And if you're a real perfectionist, you can go chasing down other terms, for example, third order terms. And there's this other, so you can imagine that just going to higher and higher order, you would expect things to eventually converge. So that's right. And so we didn't print the third order term.
Oh, thank you. Scary enough.
I think we might mention how many terms it entails.
I was just looking up. There are 56 third order.
56.
So 56 third order terms. So this is,
So does celmech do this in general? So if I wanted to take this out to fourth order, those coefficients would be auto-generated or auto-looked up somehow?
That's right. So it'll generate things to arbitrary order. The only limit, I guess, is computer memory, and evaluating numerical values for all these terms at some point becomes prohibitive as well. I guess there's a wrinkle that we mention in this application, that it's not always just an issue of going to higher order terms. Another potential correction is there's some discussion of this in 2.3, the correction from osculating to mean variables. And I mentioned earlier that usually, so there's this disturbing function expansion, and one usually discards an infinite number of potential terms. on the basis that they generate fast and small oscillations. But in reality, those fast and small oscillations mean there's a slight offset in variables like, for example, semi-major axis and eccentricity between what the instantaneous value is and the mean value of those variables. And what one is implicitly doing when integrating a model like the one used by celmech is that you're formulating things in terms of mean variables. But if you use osculating variables as input for equations designed to work in mean variables, you'll get slightly different answers.
Indeed.
And so if you really care about getting a high precision answer, correcting for this difference can be important. And there's some tools in celmech designed to account for that difference without forcing you to include all the high frequency small terms. There's a sort of analytic way to account for their effect.
Has a pretty big effect. Adding in the mean variables. Right. Moves the shift, gets the amplitude a little more right. Very nice. Very cool. And third order. Whoa. Plus mean variable. Very good.
And of course, one can have lots of fun chasing down, which term needs to go in to match this.
Sure. What is the driver?
This n-body result exactly. Which, I guess I'd emphasize, is not always the point of constructing these sorts of analytic models. If one is just looking for insight into some dynamical phenomenon, but nonetheless, it can be fun to show that it's quite amazing that these analytic models with just a few terms can reproduce, predict what you see in direct n-body integrations.
Well, let me just ask a question on that then. So in this particular system, is there any significant CPU runtime differences between running, let's say, Rebound and celmech to third order with mean variables? I'm just trying to get a sense of relative cost. Is celmech cheap? Is it expensive? Is it?
Yeah, so in this instance, actually, at some point, celmech starts to get more expensive. I believe in the case of the third order variables, in fact, it does in this case. And that's just because, integrating this large number of cosine terms and calling them in your force evaluations gets expensive. And another thing to mention is that, there's been lots of work coming up with highly efficient integration algorithms for direct n-body. celmech by default uses just a sort of out-of-the-box integrator that's part of SciPy for its numerical integrations. And so it's not particularly tuned to, one could imagine, depending on the use case that you're interested in, coming up with more application-specific integrators that might speed things along a little bit more. But there's certainly alternative advantages to using celmech, and that's it. Often insight, but also it's not always the case that to get an answer out of celmech about something that you need direct integration. Rather, sometimes you can be looking for equilibrium points of specific models. In other words, points, you're reducing the number of degrees of freedom that you're considering in your differential equations, and these reduced differential equations, fixed points, for example, can correspond to special configurations, and that can be done by root finding, for example.
Speaking of applications, we have some here.
I think going back to what Sam was saying earlier too, right? I think often when you're adding these terms and comparing to n-body, you're not trying to find a faster way to do n-body. You're just trying to figure out like what's affecting the dynamics, right? Like we discover new systems, and like discovery papers say, look, like this system is 3% away from the 4 to 3 resonance or something like that.
Okay.
And does that resonance matters? Like if it were 5% away, would it matter? And here you can just side by side set things up, take individual terms, and figure out whether for your application, the thing that you care about, which terms do you have to include and which ones matter?
Right.
Because then by sort of narrowing things down and figuring out, well, the secular dynamics here doesn't make any difference whatsoever. I can just take the resonant terms. And then you have a much simpler analysis where you can you get to check what the answer is in the back of the book before doing a lot of work on the theory, to make sure that you have the ingredients that you need to get the phenomena that you're trying to understand.
It's all about insight. Right. Very cool. I want to talk about some of the applications, coordinate systems.
Yeah, so I think beyond the introductory example, the paper starts to get into the gory details of what the code is doing under the hood.
Indeed. Let's talk about that.
And sure, but yeah, before diving into that, I'll just make a general comment that I think a lot of this stuff in celestial mechanics is conceptually not so difficult, in the sense that people learn Hamilton's equations in a graduate student mechanics class, and there's some techniques, and it's a nice elegant formulation of how to do mechanics, and it's really powerful when applied to planetary systems. I think what's often prohibitive in doing this sorts of work is the sort of technical details that go into initially formulating your equations of motion, this so-called disturbing function expansion stuff. And that's really the stuff that celmech is designed to automate for you. You can learn, I think it's best to approach the subject by sort of getting a feel for how it's used, and then later going into gory technical details about constructing the equations of motion from special expansions of interaction potentials. And so part of the hope with this code is that it actually makes these sorts of celestial mechanics calculations more accessible for a wider audience.
Right.
I've been able to have undergrads successfully do some dynamics projects with this. And Dan, I don't know if you've had any experience having students get up and running with celmech yet, but I think it really widens the audience for who can do this sort of stuff. But
Yeah.
Okay, so on to the gory details. So the way this is sort of detailing how one gets, what precisely do we mean by the variables used by celmech? How are exactly our equations of motion formulated? Starting from expressing the Hamiltonian of the system in a Cartesian system, how do you go to these special action angle variables?
Yep.
So modified Delaunay variables that's used. And of course, celmech, this has been coded up by us, so you don't have to.
But you should know what it is. No black.
You should know, yeah. So certainly one should know what it
boxes.
is. That's right. That's right. No,
By us, but mostly by Sam.
And so, equation 11 brings us to the disturbing function. So I mentioned this multiply infinite series expansion of the interaction potential. So this is expanding the interaction potential in the various angles involved in, or orbital elements involved in the planet's orbit. So you see this bold-faced theta appearing as a combination of the various orbital elements, and then here we have a tenfold sum over indices, some appearing in K, and then the news as well, expressing higher and higher powers and inclination and eccentricity.
Yes.
And
Cool.
so this has been a sort of classical thing since I think there's some famous expansions carried out in the sort of 19th century. The highest one to 8th order and eccentricities and inclinations.
Wow.
Wow.
Yeah, when it was
That's impressive.
When it was checked using computer algebra, I think they found like 2 errors out of
two or three errors in all these terms.
That's amazing.
Where one of them didn't actually matter too much. Just the attention to detail and patience to get all those terms right is just flabbergasting. I don't understand. Yeah.
Wow. Yeah, particularly at the 8th order. That's amazing. Good job. All right, so we got this crazy Hamiltonian. And we do some expansions. Variables.
Yeah. And so and I guess if people don't want to use the celmech for the framework of integrating full equations of motion and stuff, they can at least use it even to just get these coefficients that appear in this expansion. So we describe a little bit the you might have some other application in mind, but the stuff that we've set up is not perfectly suited for. And so if you just want disturbing function coefficients, here it is.
You can do it.
You can do that. I mentioned before that there's these canonical variables that we formulate our equations of motion in, and they are similar to, but not equivalent to, the orbital elements.
Right.
And so actually rewrite, so there's lots of classic expansions and expansion methods for expressing things in orbital elements, and one of the sort of pieces of work that went into this was rewriting those classical expansions in orbital elements in terms of these canonical variables.
Okay.
And you can see our coefficients have picked up, I guess if one stares closely, we've picked up another set of indices where we've expanded coefficients. In the right-hand side of 16, we now have L's expressing the fact that our coefficients have derivatives with respect to semi-major axes as well.
Yes,
and so,
good.
So I think this describes a framework for generating disturbing function arguments and calculating them and evaluating them.
How many lines of code is celmech, roughly? Is it 10? Is it 100?
A bit more.
100,000? 100,000.
I don't think we're at 100,000. I don't have a good sense for.
Cool.
It's Python. It gets lots of white space. So.
Well, okay.
It's cheating a little bit.
Well, we won't count white space, but okay.
That's right.
And GR, you take account into GR?
Yeah, you can add. So there's standard methods of including the effects of if your central body is oblate, or if you want to consider, there's some approximations that are sort of popular in the literature for correcting for the apsidal precession caused by general relativity, which actually has a really important effect on the long-term evolution of Mercury's orbit in the solar system.
For example.
For example, that's right.
Yeah. Very cool. Very cool. Wow.
And now, I guess we've come to section 5, and so this gives a little bit more detail of those workhorse classes sort of described in the introductory example, namely the Hamiltonian and Poincare modules, which these are two sort of objects that are kind of fundamental to celmech.
Indeed.
One sort of represents the dynamical state of the system, sort of like a initial data, for example. So you could think of Cartesian positions and velocities and masses, but its sort of internal storage system is based on the canonical variables rather than that, but it can use those to give you stores eccentricities and anything else you might more familiar if you want access to that sort of information.
Mhm.
And then the other one is this Hamiltonian. So there's a specialized Hamiltonian subclass called Poincare Hamiltonian that's designed to do this sort of work with the disturbing function, and it's a subclass of a more general Hamiltonian
Good.
class that we've designed that is so a lot of celmech is built on top of this nice open source symbolic computer algebra library called SymPy, and
Yes.
the Hamiltonian class itself is a nice class for just formulating symbolically a Hamiltonian and getting the corresponding equations of motion that one can then integrate and do all sorts of stuff with. And yeah, so Poincare Hamiltonian is just a special subclass of that,
Okay.
designed specifically to work with.
Here we go. Yeah. Mm-hmm.
So it brings us to, I guess, canonical transformations. Maybe I'll let Dan talk about those.
Sure. Yeah, I feel like canonical transformations is that topic that you learn in your graduate mechanics class that you have no idea what it's for, but it's actually really useful in celestial mechanics,
Mm-hmm.
right? Just because you start with so many angles, you have 3 angles for each planet, and you have several planets.
All right.
But then what you end up doing is you end up identifying only particular combinations of those angles as mattering.
Yes.
So the fact that you started with 6 or 9 angles, but only 2 angles end up mattering, implies the existence of several conserved quantities.
Okay.
And these canonical transformations are a technique in Hamiltonian mechanics for just turning the crank and figuring out what those conserved quantities are,
Good.
and to derive new variables that are still canonical and follow Hamilton's equations.
Mm-hmm. Good.
That reduce your dimensionality enormously. And that is huge for any sort of analytical understanding of the problem, where you have this huge space that you're trying to explore, which you can't possibly explore with n-body. You can't run that many simulations.
Right.
This tells you the combination of variables that actually matters for your problem.
Nice.
And I think probably we can't do a tutorial on this live. I think is the sort of thing that you sort of have to dive into, but it links to some nice Jupyter notebooks that go through how you would chain together a series of these transformations in systems that are quite complicated, right? Like chains, resonant chains.
Cool. Mm-hmm.
Yeah.
Good.
I think that's actually a really useful
Oh yeah.
thing to go through if you're trying to.
One might
really
actually
understand
understand canonical transformations a little better after going through that. Exactly what is it? Oh, Lie series transformations. Okay.
So yeah, this falls under the heading of a special type of canonical transformation that becomes particularly useful in the conversion between osculating and mean variables that I mentioned in the beginning of our introductory example. And so, that's a sort of one of the main motivations for including this Lie series transformation capability in celmech. And so it allows you to do that conversion, and depending on the model that you're working with, the Lie series method can also give you a complete solution or analytic approximation to a solution for your equations of motion. So you don't have to integrate anything. You can try solving things by Lie series itself. In particular, this will work provided there's no resonances in the system.
Yeah.
So if there's no resonances, and so this is, it's a nice tool, and there's actually a nice application in terms of transit timing variations that one can apply Louis series to predict transit timing variations. So these are for transiting planets. When there's multiple planets going around a star, their gravitational interactions cause their transit time of arrivals to not be perfectly periodic because they're no longer in a perfectly Keplerian potential from the host star. And this has been really valuable for measuring masses and eccentricities of exoplanets. And often these are modeled with n-body simulations, but there can be some pitfalls to that, or at least some numerical costs associated with it, that it can be valuable to have an analytic model for transit timing variations. And this is a wonderful way for generating them. But there's all sorts of other applications.
Very cool. Very cool. The derivative operators.
So
summary.
Yeah, that brings us, I guess, to the summary, which I guess reiterates what I've said. It's an open source package. If you've used Rebound, it'll hopefully come natural to you. If you haven't used Rebound, I highly recommend it. It's very nice code.
Good shout out. Good shout out.
That's right.
Cool.
And yeah, I hope people find this a helpful software tool.
Yeah. And
yes.
Go ahead.
Been a huge amount of work with almost all the heavy lifting done by Sam. I think generations of grad students are going to construct statues.
Of Sam.
Yes, exactly. Yeah.
Or celmech. Very cool.
And
just so people know, there are 3 appendices in this article. Appendix A is perhaps the most useful, as we got an actual symbols of what is being used on all that.
I can say a word about what each one is. So as you might have noticed scrolling through, there's lots of symbols cropping up, and
it's good to have this.
Somebody who doesn't work with these day in and day out, I can imagine you get lost. So you can always come to the appendix and say, what is that? What does this capital X mean again? Or what's this funny C with a tilde over it? And,
with the news and the K's and the L's. And all very cool.
That's
very cool.
Right. So that's a quick reference for that. Appendix B is working out some disturbing, a little piece of the disturbing function expansion that has been, I think some elements of this are actually novel, as far as I know, for representing so-called indirect terms. And yeah, as you can see, all sorts of special functions and series cropping up.
Nice.
That one works through once and then hopefully never has to again.
Awesome. Very cool. And with a little orbital element to canonical variable.
Yeah, and Appendix C addresses this problem that I mentioned before, where a lot of classic expansions are developed in terms of orbital elements. And if you want equations of motion in terms of canonical variables, you need to relate the 2 expansions. So this appendix does that explicitly.
Cool. Very nice. Very nice. Sam, Dan, thank you so much for walking us through your lovely article and your new open source software. So let me ask, because it's usually the case that by the time an article comes out, it's already behind the software. Software has already moved on, if it's an active project. So where do we go with this over the next couple of years? Is there going to be a celmech 2.0, both in package and in article? Are there additional features that one would like to add to celmech? Can we handle bringing in direct measurements of a system, for example, or something along those lines? So just kind of in general, where does celmech go over the next 2 to 5 years, let's say?
All of the above.
Okay.
I don't know about this, so I'll say that there are certainly features that are already a part of the code that were not documented in this initial release paper that will hopefully be documented in a feature paper or part of an application paper, perhaps. I'll just mention a couple of them. One is there's some special machinery in celmech for doing integrations of purely secular equations of motion. So these are the sort of what Dan referred to as orbit averaged equations of motion, where you sort of considered the dynamics of the planets as the sort of smearing out their mass into interacting wires is often the way it's described. And so, yeah, there's a sort of dedicated, there we know we've done a little work on implementing our own integrator designed to do these. And the advantage is that often one can do much faster numerical integrations of the system you're interested in, which is especially important for a lot of exoplanetary systems where, given their orbital periods of, a few tens of days, perhaps, direct n-body integration is really outside the reach of even things like rebound, if you want to do them for billions of years.
Yeah.
So.
Okay. Yeah, and we actually didn't cover that, right? The time scale.
Yeah. Another module that's in there now is some stuff for sort of looking in detail at the dynamics of resonance systems, taking a slightly different approach to the one described in the paper. So rather than expanding in powers of eccentricity and inclination, one can construct equations of motion that are derived semi-numerically that govern just the resonance dynamics. And this is done by numerically averaging or doing some numerical integrals of the interaction potential, and leaves you with some ways of investigating. So these are nice for investigating the dynamics of resonances.
Cool.
So, and yeah, we've certainly designed the code to be something that can be continuously in development. So always adding stuff.
Well, three or four papers at various stages of writing.
There you go. Very good. Well, I wish celmech a happy and productive life over the next 20 years, let's say. Very good. Or 40, take your pick. 40. I like 40 years. So. Very good.
Sounds good. All
right. Sam and Dan, thank you so much again for walking us through your very lovely article and your new open source software package, celmech. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you, Frank.